Hello everyone, my name is Orithro and today I'm going to talk about Forgeformer. It's a transformer with an asterisk to add two two-digit numbers. But the thing is that this transformer has not been trained, all right, on any GPU or CPU. I have written down the weights by hand myself on pen and paper. So too long don't read. You can demo the thing at this link. It will be in the description below, and you can read about it or feed it to your favorite LLM and explain you at this link. All right. So let's get started. First of all, why on earth would I do this? I have a GPU, I have computers, I have Google Colab, I can just train using the normal training procedures. But why did I decide to write down the weights by hand? Well, recently I worked with a professor of mine on explainability of vision transformers. And while doing this research, I ran into this thing called saliency maps. So, which are like attention heat maps, which show you where the model was looking at while doing some task. All right. So, naturally, I dug deeper and into this field and I discovered mechanistic interpretability. That's a mouthful. So, I'm just going to say mech-int for the remainder of the video. And again, thank you, Neil Nanda, for this amazing topic. Now, mech-int is aptly called the neurosurgery of models, which sounds very fascinating to me because I've always been intrigued by how the human brain functions and how I can program my computer to act like a brain to some extent, of course. So, mech-int is called the neurosurgery for models because it goes deep into the models. And now, before we even go into the depths of the video, I would like to kind of give a warning that if you are not at all familiar with linear algebra, matrix multiplication, or you don't have too much idea about transformers, attention mechanisms, I think a little bit of brush up is good. I will explain everything in detail, but a little bit of familiarity will be very very helpful for you. I will be explaining stuff, but it's better. So mech-int actually goes into the models, and all models have weights inside them. So these are like little numbers which change your input into the desired output. So these numbers are mostly matrix multiplications. There are lots of operations, but generalizing, I can say they are linear algebra operations. So I will spend a little bit of time explaining what this is because I think it's crucial. So if you look at the paper of how these models work, you can write out almost exactly what happens when you give an input. So if you like have the source code of a model and the weights, and you input a sentence, let's say the cat goes to the market, you can convert that to embeddings, you can do the operations, and you can get the output as well. You can track every single linear algebra operation that results in the output. But you cannot map this to the human understandable topics. So I will use the vision transformer example, which works on images. So let's say we have a vision transformer, which is responsible for detecting if an image is that of a cat or a dog. So how does a human do this task? You look at the image, you say, okay, it has ears, it has this type of a face structure, it is the body is like this, the cat is making purr, the face, it has whiskers like that, it has nose like that, etc., etc. So, broadly generalizing, you can define a task, which is, let's say there's a task which is done by a model as well as a human. In the human case, in most of the cases, the task can be broken down into subtasks, which the human performs to, get to the final result. But in our case, we only have a series of floating point or linear algebra operations. So, how do we bridge the gap? How do we translate the linear algebra operations into human understandable subtasks? That is the goal of mech-int to some extent. I will use an example which I have shamelessly copied from Neil Nanda's presentation. It is that for centuries, humans have engaged in farming, not aura farming, crop farming, where rice is planted and grown. So, for centuries, humans have planted rice grown the crops and eaten, but they don't know the entire procedure of how that happens, right? So it was only many, many years after this farming started that we understood botany, photosynthesis, and other concepts of how it was mapping to the actual procedure why we were able to grow crops and harvest them in the first place. So, making is kind of like that. We know how the model works in terms of linear algebra operations, but we don't know kind of the how in terms of human understandable tasks, how it performs a certain task. I hope it was clear. It's a little bit of convoluted explanation. I think I did not do it as much justice as Neil, but yeah. And last reason being, it was an academic challenge which never bores me, and I was intrigued to do this task for a very, very long time. I had exams and I had interviews, so I was really, really busy. So finally, I decided to, sit down, drill down, and get this job done. All right. We shall now look into the architecture of the Forgeformer. It's called Forgeformer. Let's say, let's look at the architecture of the name first. It's called Forgeformer because the weights were forged by me by hand. All right. So, in a transformer like model, there are some architectural decisions that are to be taken by whoever is making the model, in this case, me. So, you have D model. So, if you have read the transformer paper, D model is a very known name to you, but of course, I'll go into depth. What is D model? Uh, the model can be thought of a machine which transforms its inputs to vectors. And linear algebra familiarity is really required. I will not go into depths of what a vector is. So D model tells us the dimension of the vector space in which the model will operate, in which the tokens will be converted to vectors as. Now, the model will operate always in a D model vector space is a wrong thing to say. In our case, yes. In the general transformer case, no. That will be explained in point 3. So D model is chosen as 3 here. Why? Now, normally it's 512 and big values, but of course, I'm going to derive this matrix by hand. I need to, not be sadistic and masochistic. So 3 is a reasonable number. But 3 is not chosen because it's easy for me. 3 has a very specific significance that I want to clarify. So the reason why I chose 3 is because you can visualize it as this bar with 3 sections: one, two, three. The first part, I wanted to store information about carry. So whenever we add 2 digits, there is a carry. There can be a carry, right? So in the units place, let's say we add 3 and 7. One is a carry. So one position dedicated for carry. One position I want for the digit magnitude itself. So when I'm representing a digit, it has a magnitude, right? I want that dimension to represent that magnitude. Lastly, one dimension for position. This is important. If you are familiar with the attention is all you need paper, they have a separate they have learned embeddings and positional embeddings which they add. I do not have a separate positional embedding. Instead, I'm using one of the dimensions to denote position. How am I denoting position? Plus one for the first index, minus one for the second, and so on. Periodic. We'll again go into that later. Why periodic? Why like this? The input token length is fixed at 5. Yes, 5, not 4. A, B, C, D, the 4 numbers, A, B plus C, D. So basically, if we take our example of 17 plus 25, 1 is A, 7 is B, 2 is C, 5 is D. We list out those numbers, and EOS is the end of sequence token. The EOS token will be of paramount importance throughout this entire talk. So I will talk about it in very much detail. The 5 digits, you will ask a question, why not plus? So, like, since our transformer is just doing addition, plus is kind of redundant. So, I'm just getting rid of that without plus. And of course, you can say that C and A can be 0. Yeah, so this supports single digit numbers as well. The addition to be performed, yeah. Yeah, point 3, which will explain why this happens. Layer norms. you can see in the standard FFN paper, there are layer norms. FFNs, standard attention paper, my bad. You can see layer norms. There are FFNs, feed forward neural networks. And the embedding and unembedding are done via matrices. These are absent here. Now, why is it absent? I'll go into depth. The goal of this entire academic exercise is understand how attention layers correspond to human subtasks when the model and the human is performing the same task. The remaining parts of the transformer, I am not so interested in. I am just interested in the attention layers only. I want the attention layer to do the maximum amount of work. The FFNs can handle nonlinearity very well, but I want the attentions to take care of that. I have to stack how many layers? I don't care, but I will stack attention only. That's the first goal. Embedding matrix, I am not using because again, every single matrix, embedding matrix is basically a learned matrix, the learned embeddings. I have to write that by hand, which is cumbersome. And secondly, the approach that I went here pretty much works. I've tested, of course, so I know, but even from a pragmatic point of view, it should work because it's containing and encoding all the information. Unembedding matrix is very, very crucial because a model outputs usually logits, which is basically probabilities per output token. And the unembedding matrix is responsible. I think I'm messing it up. The unembedding matrix takes the final output and converts it into token logits. That is the thing. All right. We don't want that. And this will become very important when we talk about the last output layer because there's a little bit of cheating that's done there in the unembedding part. We'll get to that later. Architecture part two. There are two attention layers. Two. Why not one? Why not three? Now, my reason for choosing two attention layers is actually something that I picked from elementary grade math in school. When we were taught two-digit number addition, we were taught to add the units digit first, write the units digit of the result, take the carry if any, add the tens digit of the existing numbers, add the carry, and write the result. So if I were to take this algorithm and convert it into two distinct subtasks, I would get unit digit adding subtask and tens digit adding subtask with an intermediate task of carry. But the tasks are basically two. So I want one attention layer per task. That is clear. And this is like the overall flow. Now, a very crucial thing. Mech-int usually involves getting a trained model and then sort of reverse engineering it to figure out which layer does what. But what I am doing is not quite the reverse of mech-int. I am labeling what part of the model is supposed to do what and I'm assigning weights. So if mech-int is the reverse engineering of a model and I'm reverse engineering mech-int, then I am just training a model. You would be correct because I am just assigning weight matrices to the model, which is what training does. Training assigns the weights, proper weights to the model. I am also doing that, but I am doing it from a mech-int point of view. So initially, I have control of which attention layer is going to do exactly what, and I'm going to assign the weights to it that way so that I can analyze the path taken by the input to the output. That is basically mech-int is to some extent. Again, this is how I am studying mech-int. This is not the right or the best or the most optimal way, but this is what helped me understand concepts. So I'm going to use this. A thing though, which I'm going to use my blog for. Everything is going to be in the link. This is a wonderful tool. We'll be coming back to this later. There are certain nuances which I explained here. All right. I want, if you're really pedantic and certain details are bothering you, I need you to read this part. It will be in the description and everything is explained here as well. There are certain things that I've done which deviate from the standard transformer architecture, but that is crucial for the way I want to understand the attention layers. Yeah, this is the slide. So now we are going to look at how I made layer one. Lots of scary math, lots of numbers, but I'm going to break it down into as simple concepts as possible. So remember this EOS token that we talked about? So EOS basically means end of sequence. So its only job is to like tell me, okay, That's all. Sequence has ended. You would be correct, but it also serves another purpose. The EOS row will actually store the result. What do I mean by EOS row? Let's get into that. Our example for this entire talk would be 17 plus 25. It's a nice example, involves carry. So you can see, according to our embedding scheme that we discussed, one dimension is for digit. So 1, 7, 2, 5. First one is 1, second one is minus 1. This is the positional embedding that we discussed. The carry is initially 0. We have not done any addition. We don't know what carry is going to be there. You can see that the EOS token has 0 carry and 0 magnitude. So this, of course, this denotes that the sequence has ended, but this row will also be used to store the final result. So after the entire linear algebra operation of all the layers are done, we are going to look at the last row and we are going to get the answer. That is what will happen. You can wait and watch. So these red matrices, these red border ones, are the one I derived, and I will tell you why I derived it like this. Why 10? Why here? Why minus 10? Why it is here, not here, not here, not here? I will discuss everything. But let's first talk about how this interaction comes about. Note, it is written KQ here. However, this matrix is actually Q times K transpose. This is an error in this PDF, in this presentation. Everywhere where it is written KQ, it is actually Q times K transpose. I apologize. So I will use an example, a sort of physical world scenario to explain what happens. The K, Q, and V, you might have seen them before. They are basically the key, query, and value in the attention mechanism. Now, what do they do? It's a very nice thing. So let us visualize that a man is standing on a hill and through a megaphone he's shouting, I want everybody who is at a certain position, please reply to me. And he's standing on top of a very high hill, okay, a tall hill. And there are small, small hills or equally taller hills or larger hills, doesn't matter, around him. So his megaphone message travels to everybody. Now, all those people in the other hills who are on the positions that he's asking for will use their megaphones and reply back, yes, I am present. And the ones who are not will reply nothing. Attention basically involves, in the KQ part at least, involves Q shouting for certain positions and K replying back that there is something present at that position. So we want a high score there. How do we implement this? So the way the key and query matrices are derived is by multiplying the input embedding matrix with the weights. So to get Q, we multiply X times the weight for Q. To get K, we do the same but with weight for K. Why did I do this? When this gets multiplied, you see we get this matrix. When this gets multiplied, you see we get this matrix. Okay. When we do the Q times K transpose operation, look at this matrix that we get. Okay. Look at this matrix that we get. 100, 100. Do you know what positions these are? Take a look. The second position is the digit 7. The fourth position is the digit 5. We are getting high scores at second position, fourth position. Initially, I had said that attention layer 1 is responsible for addition of units place digits. I am getting high attention scores here. Now, this is not exactly attention score because it has not gone through the softmax yet. It has not been dot producted with V. But let us already start to see that there's a high score for the desired position. I hope my example was clear. Now we shall look that once we have derived the position part, how to get the value at the position. For this, we are going to use another analogy. For a moment, forget about men on the hill. All right. Let us look at this. You go to a librarian and you say, I want to learn about reptiles. Fair question to ask. The librarian is basically our KQ. It does all its shouting. So basically, a librarian will walk and look at the shelves or use some sort of system. But we can sort of to draw a parallel with our previous example. We are going to talk about KQ being the librarian who shouts to all the books that, hey, all books, books who are about reptiles, can you talk back to me? And every book which is about a reptile uses their megaphone to scream back that, hey, I'm a book about reptile. I am on this shelf, this aisle, this row, this cabinet, etc. And we get this high scores for places where reptile books are there. Now, the librarian won't help you get the information. They'll give you the books. It is up to you to read those books and derive the knowledge. So this V matrix is actually this V matrix, which is done by multiplying the X matrix with this matrix, we get this, is actually for doing that. And you can see something. 7 and 5 has been doubled. This is literally the double. All right. Why double? We'll go to that. Now, the formula for attention is softmax of this matrix, the softmax function. Again, I'll expect you to be familiar with this softmax function. I have not written it and I will not write it down. This will go into the softmax function. Row wise softmax will be taken. Every row will have a softmax. We get this. This attention one times this will be the output of our attention part. I want you to look at this matrix. And I want you to look at the underlying values. And I will tell you something. Attention is like quantity that you have, a limited amount of things. All right. So far I was talking about a boring lecture, right? You might start to deviate your attention somewhere. Now, if you were to quantify that, how would we talk about it? Let's say attention is a number, the sum total quantity you have. All right. I'm doing something here. I'll show you. Let's say you have 1.0 units of attention. Your attention can range from 0 to 1. All right. Because my lecture is very boring, you don't like it at all. It's so boring. White slides, lots of numbers, matrices, no funny graphics, no memes. Your attention deviates to Instagram reels or something, you know, like reels. Yeah. You start watching reels. So I can say that initially your attention towards the lecture was 1.2 because I talked about all sorts of analogies and people shouting on hills. But as the math came, your attention became zero point 0.8 towards reels and zero point 0.2 towards the lecture. Now that I've again talked about this, I am talking to you directly about watching the reel. Your attention towards the lecture has become zero point 0.9, and maybe towards the reel it has become zero point 0.1. So it's sort of an analogy. What I want to illustrate via the analogy is see. At position 2 and position 4, what was position 2 and position 4? 7, 5, the units digits. We have equal attention, point 0.5, point 0.5. So our model is paying equal attention to the units digit, which is what we wanted. We wanted the model to add the units digit. So when you are adding two digits, how much attention will you pay to each digit? Equally, so that you can add them. That is what's happening. Now, softmax actually creates a probability distribution, and and since we said row wise probability, so sum of all values in the row should be 1. There are two units digit, so it is point 0.5, point 0.5. So if we were to just directly multiply, the value would become half. We don't want half, we want the full sum, right? That's why the 2 is here. So that when this multiplication occurs, this 2 and this half offsets so that we get the desired magnitude. There is no scaling involved. That is about layer 1. Whoa, slow down. Lots of scary math. I will break it down again. It's very simple. It's a summary of what we've discussed so far. X1 is the initial matrix, 1, 7, 2, 5. These are the matrices that we discussed for the weights. This is a key value query. We get the key query value matrices. Again, there is a bug here. This will be 2. This will be twice the value. This is singular. A little bit of typo. This is the Q again. Q times K transpose. This is the attention. This is the output. and we add x1. We have not talked about adding x1 ever. Why did we add x1? So this is called residual connection. Now, what is a residual connection? Actually, what happens if you have, again, a little bit of familiarity with the Vaswani paper would help. That paper stacks many, many, many layers on top of each other. And in popular models, the ones that you might use today, they have residual connections with many models stacked, with many layers, I beg your pardon, stacked one on top of another. So what happens is, you can see in a single layer, our input matrix undergoes so many transformations. And in this layer, all the transformations have been done for the purpose of adding the units digit. All right. So by the time we get to the output, the matrix has been somehow manipulated to suit the task of this layer, which is adding the units digit. If this goes to the next layer, whose task is added to the tens digit, maybe some of the data is manipulated in such a way that the next task can't be done properly. We want the original matrix values, the original signal, to be strong enough so that whatever manipulation we did here remains, but also the signal is strong enough so that the next layer can use the original signals for whatever purpose it is, and it may be different from the previous layer, which it is in our case. So we add the input signal here. So in every layer, when we do a residual connection, after the output of the layer, we add the input to it before giving it to the next layer. This basically creates a sort of communication bus where you can visualize each layer taking the input from the residual stream. It's called the residual stream, not the bus actually. Take it from the stream, do some operations, write it back into the stream, and this goes on and on. Wonderfully explained again by Neil Nanda in his video about the mathematical framework for transformer circuits. You can get the link from my blog, or I'll link it in the description. So this is the thing that goes into the next layer. A question that I had and you should be having is that, okay, this guy has been yapping for the last 20 minutes, but where is the output of the units digit? Like, I added the units digit, there should be a 2 and a carry of 1. I can't see anything in the US row. This guy said answer will be in the US row. Yeah, I had the same question. But the US row will contain the output after the model is done working. Think of it in this way. If you are solving an answers on an examination answer script, and after 1 hour, in an examination of 3 hours, after let's say 1.5 hours, I take away your answer script and say, hey man, you have not written the answers. Is that fair? So that's what you're trying to do. The model has not finished working yet. So we are saying, hey, have you done? But the model is not done yet. So we should wait. Now we will go to layer 2. Layer 2, same analogies apply. The man shouting on the hill with a megaphone. But this time, he is not shouting for positions with -1. He's shouting for positions with +1. Now, there's a slight nuance here that will be a very, very big problem. Not a problem, but very, very different from the previous line. What was happening in the previous line? We knew that units digit are at positions -1, -1. So the man on the megaphone can ask, hey, everybody who is at position -1, can you shout to me? I want to know if you're there or not. And they shouted back, or everything was happy, wonderful. Now, if we do the same, that, hey, everybody at position 1, can you talk back to me? 1 will come, 2 will come, which is okay. They are the tens digit. But this 0 will also talk back. This 0 will also talk back because it is also at position 1. But that 0 corresponds to the magnitude of US token. We don't want that. Now the task is addition. Now the task is addition. So in addition, adding the 0 won't make a difference. Absolutely fine. So we should not care about that. But there will be a problem, which I will show to you after some minutes. So let's focus our attention, pun intended, on the query weight and the key weight matrices. If you recall in the previous layer, yeah, 10 minus 10. Key had -10, query had +10. Now all of a sudden we have both positive 10. Why? Why the sign change? It's trivial. Earlier we had 1 minus 1. So let's go back to that slide. Earlier we had one minus one here. So in this whole multiplication, this, I want the value to be high because I want to give more attention to those positions. That's why I need one minus sign here, which will make the overall thing positive. And since these were positive, these were positive, the tens digit, this minus makes them negative. So we get low scores. Here, these are positive. So these positive numbers give positive scores to the positions that we need. And since this one is minus and these are all positive, we get negative, low score for the units position because we don't care about that in this layer. Again, trivial multiplication. These multiplications give us this. Again, this is a typo. Q dot KT gives us this. Now, I told you a few minutes back that I'm going to talk about what is the problem of getting this zero. You see how we get 300 here? The attention for every row is 1. But earlier we were splitting it between two tokens. So we got zero point 0.5, zero point 0.5. Now we will be splitting it between three tokens. So every token will get one third attention. What will that impact? It will impact this. Earlier we had 2 because the factor was zero point 0.5. Now since we are giving one third attention, we need 3. We need 3. 3 will make sure that this multiplication gives us this times this will give us 1. So that the final magnitude is good. What do I mean by good? Look at this. The value matrix. Low values and high values. We have the values we need. And when we multiply this attention with the value matrix, when we multiply this attention with the value matrix, we get this. And I get the answer. I get the answer. Now you say, hey, where is the answer? The answer is 42. 17 plus 25. Look at this. The EOS row middle dimension is for digit magnitude. And in this layer, what have we done? In this layer, what have we done? We have added the tens digit. So if you recall, 17 plus 25, the addition of the tens digit is 3. 3 is here. Ignore the positional embeddings. We don't need that for the, for the result. We have 3. But we get 12 here. 12 is not a digit. Recall something. 7 plus 5 is 12. The sum of the units digit is stored here. So the model has utilized the 2 dimensions. Now the carry is always here, right? In the units dimension. There's a nuance where the carry can be in the tens dimension. We'll go back to that. We'll go to that in the future slide. So 12 is here. Now the final task remains. Get the number out of this output matrix. Again, overview. We get this, we get this, we get this, we get this. 12, 3. Our goal is to now get 42 from this. And most importantly, how is 42 stored there? All right. Ha. Again, I will go back to the original motivation for this project. The motivation for this project was to understand how attention heads perform subtasks, human corresponding subtasks. And I wanted to do that by handcrafting the weights to show how the attention heads might do the human tasks. That I have shown. Instead of using the unembedding metrics, which would again add another computation weight to my pen and paper process, I have done a clever trick which unfortunately uses the plus operator. So basically, I'm just adding the damn thing. I could have just done a plus b, but no, the exercise served its purpose. We saw how the attention layers are performing the distinct tasks. What I do here in this code, it's lifted and shifted from the notebook that I have. Everything in the description below. -1 basically means the last row. 0 means the first dimension. 1 means the second dimension. We access the unit sum, which was 12. If it is greater than 10, which means there is a carry. So carry is 1. And we subtract 10. So from 12, we subtract 10. We get 2. 10th sum we have. We add the carry to it. So 10 sum was 3 plus 1, 4 times 10, 40. Plus the unit sum is now 2. 40 plus 2, 42. That is how we get the result. We could have used the unembedding matrix, which would conform to the standard, transformer architecture. but I chose to do it this way. Before the takeaways, I want to do a short recap using my demo tool, and I will advise all of you to play around with it. If you are really serious and intrigued, I will advise you to play around with this. All right. So I'll go here. This is the link. I will add this to the description again. So yeah, already our example is preloaded, but I will just do it with a different example. No, answer will be like, see. So we see 1626. All right. These are the tokens. We are converting that to vectors. 0, 1, 1 is for the digit 1. 0, 6, minus 1. 0, 2, 1. 0, 6, minus 1. EOS. This is how the matrix looks. These are the weight matrices. Again, you can confirm this from the slides. Slides will be also given as a PDF in the description. Do check them. These are the query key value matrices. This is the QKT. It's written correctly here. I made some horrible latex mistakes in the slide. These are the values. This is the after softmax. You can see how 50-50 attention is split. Residual output is basically adding. So attention times V gave us this, and this is the residual connection output. The US row is highlighted. You see, after the residual connection, 12 units digit is stored here. Layer 2 weight matrices given. Here it is given nicely. This is for the layer 2. This is the QK transpose matrix for the second layer. You can see how it's just highlighting the values. Again, the attention is split across the three tokens. We show that here. Now this is the final readout. You can see that the last row had 12, 3, same as the previous example because 17, 25, 16, 26, same sum. So we detect the carry units is adjusted to 2, 3 becomes 4, and we get the output 4 times 10 plus 2. This is a wonderful demonstration site I have built. It helped me while understanding the concept. It will definitely help you. Works on phone as well. It's just a simple static site, no login, nothing. Please utilize it. Takeaway. Now this is written as takeaway, but it's mostly what I felt I should do more to kind of drill down the concept into my head as well as yours. Expect a future video and write-ups about that. Properly implementing the 100 carry. What do I mean by that? Let's come to here. Let's come to the site. Let's write 99 plus 7. 106. Correct answer. Should not be worried. But technically, I did not have enough space in the embedding vector for two carries. But how did it work? The only reason it works is that we cheated. We cheated in the unembedding process. So what happens here, you can see, tens digit is 9. Units digit is 16. Okay, 9 plus 7, 16. So this 6 comes out. The 1 goes from here into the 9 and the 10 is done. This 10 is done because we are using the plus operator. Is because we use the plus operator. In a true ideal sense, we would not use the plus operator. The model would give us the answers, but we use the plus operators. So that is why this thing is happening. Oh, yeah, this thing is happening. So you can see the 100 part is working, but that's kind of cheating. I will fix it. But for the exercise of this task, attention heads doing each of the subtasks, unit digit adding and tens digit adding, it was doing perfectly fine. I want to add FFNs and layer norms, at least one if needed, to see how they contribute intuitively. I want to see the way I did using man shouting analogies and librarian analogies. I spent a lot of time coming up with them to kind of convince myself and to convince you guys. So I want to get intuitive understanding of how FFNs and layer norms impact. I want to generalize this approach for n digits and m digit addition. If need be, I'll use computer trained models, of course, because it's kind of pointless to scribble out weights after weights. It's better to use computer weights if they are very, very large matrices. I want to carry this is, I think, one of the most important points. The entire motivation which drove me to complete this project is I developed some concepts about how the heads should work while doing these tasks. I want to check if the attention heads of some open source models also work in the same way while doing the same task. Let's say I will download some model and do the same addition task, and I want to look if their heads are also doing the same thing. Heads layers. I want to train the same model as this Forgeformer, but using Pythons, standard gradient descent process, and see how those weights differ from mine. I have an ideal sense of weights. Will it be the same? Will it be different? If different, how? Will they have same eigenvalues, etc. The analysis. And I want to carry out this whole exercise for other tasks apart from addition. Some language tasks, perhaps. Some vision tasks, perhaps someday. I want to carry out because I felt this to be an incredibly rewarding exercise because of the amount of intuition I developed. Thank you for the presentation. A couple of things before I leave. Yeah, this is the blog post that I've written. It has much, much more detail than this talk. It has all the intuition, all other motivation, and it has nice explanation behind the design, the nuances, why I have chosen what values, why I have placed them there, why it is two, why it is three. Everything in the video, but much more in depth. There are takeaways, there are future tasks, everything is there. You can read this. I will link it in the description. The code is open source. I can do a code walkthrough, but it's pretty trivial. You can also see the states. All right, I have implemented this function. You can just run this in Colab or download it and run it locally. It's very small, will run on CPU. Shameless plug, my website will also be linked. So if you want to look at other projects, you can do and reach out to me. The demo will be given, the blog will be given, the GitHub will be shared. Uh, this will be given. I will be posting this on Twitter as well. So if you're on Twitter, engage, and if you find this useful, share it with people. That will be all. The slide PDFs will also be linked, and that's it. If you're an expert in the field and you find some mistakes in what I've understood, if you find that my examples were helpful, anything, please do reach out to me. I am chronically online and I will reply back to you. Thank you. Have a nice day. I hope I could be useful.